Okay, for those of you who don't know, that's one example of the problem. Okay, basically you got 3 sticks over there. We call pack, PEG. We got 3 packs over there, and you can see the disk over here. I got 8 disks over there. The way you arrange the disk will be from the smallest on the top all the way down to the largest at the bottom. It's got to be in this order. And how does the game play? Okay, so here I say given 8 disks. In general, it can be n disks. N can be either 1 or 0 or 3, 8, or even 64. I'll talk about the magic number 64. Okay, I'll talk about it. All right, so you got 3 packs over here, and then here's the rule. Whenever you want to move, you don't really move the entire tower. You only move 1 disk at a time. Whenever you put a disk into a pack, you cannot really put anything that's larger on top of something that's smaller. Okay, so these are the only 2 rules you have to follow. Our goal is this. I want to move, for example, all these 8 disks from one pack into another pack. Of course, there will be many intermediate steps. All right, that's the problem. And of course, very simple definition here, but let's get some intuition. Let's try to solve Tower of Hanoi right away. All right, let's now do that, okay? I got 3 examples to show you. Either there's only 1 disk, or you got 2 disks, and also we got 3 disks. All right, let's now do one by one. When you only got 1 disk, that means I put this, I only call A. So A, we assume is always the smallest, okay? If I only got this A on pack number 1, I want to move that to pack number 3. How many steps would it take? Just 1. All right, that's easy. Oh, sorry. Move it here. 1 step. Easy. And slightly more complicated would be this one here. If I somehow want to move, I cannot move 2 at one go into pack number 3 right away. So there is some very important terminology that will be the key to understanding the solution. In order for me to move the entire tower into P3, you can see here we say go from P1 to P3. The remaining one is something what I call intermediate pack. Okay, just remember that terminology. We're gonna need an intermediate one for us to define some solution recursively. Okay, I'm gonna make an annotation here. Just say P2 over here. This is something we call intermediate. And the tricky bit is P2 is not always the intermediate. Intermediate can be P1 or can be P3. It depends. All right, it really depends. Let's say for now, I want to move this guy here conceptually into here. So what I would do is I may just say I can move this one here first, and then move this one into here, and then move this one here to here. So you can see I somehow use the intermediate as a jumping stone, basically, right? That's how I solve the 2-disk problem, which is also not too bad. And now things will get slightly more complicated, right? I'm not talking about any strategy just yet. All right, I'm just trying to show to you how you can play with it. How about this one here? 3-1, okay? So let me try this. Maybe I would say I can put this one here, this one here, this one here. So what I have done here is kind of halfway. I managed to move the sub-tower, which is a strictly smaller problem, from here into something that's intermediate. Because I want to move from P1 to P3, so I try to move some strictly smaller tower into the intermediate pack first. After this, I'm just going to move this bottom guy into here. I'm not done yet. Think about I got another half of the work to do, which would be I need to solve another strictly smaller problem here. I want to somehow move this guy here from P2 into P3. And now, which one will be this intermediate pack? P1. Whatever that's not the origin or destination should be the intermediate, right? That sounds insight. All right, so how do I do it? So I can move this guy here. I can put it here, and then put it back. Oh, sorry. That's a bit tricky to really move that. There we go. All right, that's a play. And of course, for those of you who might be interested, feel free to try 4 disks. All right. Now, I want to show you something quickly on Java. So this is how you can play with the code. The code has been implemented for you, so all you got to do is play with it. Okay, I'll show to you. So if you go, this project is already on the lecture site. It's called Tower of Hanoi. And you will see under the model package is actually a class called Recursive Helper Method. So there are 2 methods there, which I'm going to explain to you. So you can see only 1 line for the first method. And for the second method, also not many lines, only that. So pretty concise definition, but we're going to go over that. And how do you run it? I created basically a console tester over here. We're going to run it, but there's another JUnit test case, which I encourage you to also take a look. I kind of show you some kind of pattern for you to kind of test console output, system.out.println. Take a look. It's going to be useful, maybe for Java programming in general. Okay, I'll leave that exploration to you. And if you try to go to the tester here and then run it, that one there is actually going to show you the solution for various problems. Let me just show you how you can read it. For example, you can see if you're trying to move 0 disk, nothing to do, empty, no step to follow. If you just try to move 1 disk over here, the program tells you you just got to move the disk A from pack number 1 to pack number 3. All right? And then the one I just illustrated is about moving 3 disks over here. That one there basically is going to, the first 3 steps correspond to what I said halfway done. And then after another one, moving the bottom one, we got another half over here. Right? So there's a perfect correspondence to how I solved the puzzle, which I didn't really tell you, but I'm basically following some systematic strategy, which I'll show to you how to do it. All right? And also, as a look ahead, so I'm going to show you the strategy. I'm going to show you some legend that's associated with Tower of Hanoi, just for your information. And then we'll analyze the Java code, visualize it, we'll trace it. And there's also one more thing I want to do today, which is not going to be exactly covering the exam. We just do some runtime analysis. I want to give you guys some flavor about part of what you're going to do in 2101, the data structure course in the winter. That's something you will have to be very careful in doing, but I can give you guys some idea about how it can be done. All right, we'll get one by one. All right, so that's about Java code. Please take a look if you're interested. Okay, some legend before we dive into the strategy. Okay, so for those of you who are familiar with the Indian culture, please correct me. I got very superficial understanding about the culture. So Brahmins, it's like maybe some workers in the temple somewhere in India. They have been carrying out some movement, so-called Sacred Tower of Brahma. That one basically is like a tower of Hanoi. The only difference is, rather than having just 1, 2, or 3 disks, they got 64. 64 disks. All right, 64. Something like this, right? You can see some worker there. They're trying to basically got 64 and trying to move from one pack into another. And they have been starting doing this thousands of years ago. They have been doing this already. And there's a legend there saying that, of course, they follow the same rule, which I just illustrated to you. When they are done, it will be the end of the world. That's the legend. So what we're going to do today is mathematically, how long is it going to take them to really finish that movement? Hopefully not that soon. I think you need to have your exam first before that happens. Hopefully, right? All right, so anyway, we'll take a look, right? That's a legend. I'm not too sure if that's really true, but we're going to have a critical mind about it mathematically today. Okay, so let's now take a look. Let's now talk about the strategy first. So there will be 3 phases, like 3 critical steps. Let's say you have n disks. You want to somehow move the n minus 1. So think about n minus 1 is strictly smaller than n. It's a strictly smaller problem that we want to solve. So think about what I did earlier was this. So phase number 1 goes like this. I want to move this guy over here, ultimately from P1 to P3. Phase number 1. I want to move everything but the bottom one. So this strictly smaller also tower, I want to move it from P1 to the intermediate pack P2. So after all these 3 steps, I will achieve that. Okay, so think about this here is the after phase number 1. Okay, so we start with this. After some step in the middle, we're going to reach the end of phase number 1, in which case we have moved the sub tower from P1 to the intermediate pack. Okay, that's phase number 1. And for phase number 2, according to the slides, we're going to move the bottom one, the largest one. All right, the way to move it is, so after phase number 1, we got this. So we're going to move this bottom one here to the destination, which means we got this. So this will be the start of phase number 3. For phase number 3, you can see here we got the sub tower here, but it's in the wrong pack. So we got another problem to solve, which is strictly smaller. We want to move this sub tower from P2 back to P3. And it will take certain steps over here recursively somehow, and this will be the ultimate solution. So 3 phases. Phase number 1, phase number 2, and phase number 3. Okay, but I'm gonna dive into details more. But conceptually, just remember you got 3 phases for the Tower of Hanoi. It's a very systematic strategy for you to follow. You can solve any arbitrarily large n from 1 until 64 or even larger. But we're gonna analyze at the end how efficient it is, right? We're gonna see at the end. But let's understand the correct solution first. All right, let's now go over the Java code. Okay, Java code will take quite a bit of visualization, which I think you guys should really understand first. All right. So the Java code is going to be the Tower of Hanoi. That's the method, and this will be the public version. We simply represent the disks over here by a string array. So think about if this conceptually is the tower. You can think about that's the top elements, that's the bottom one. So convention is the smallest to largest will go this way. And for the array, the smaller to largest will go this way. That's our convention. That means over here, think about when we do the recursive call, we're going to say from and to, like the pattern that we learned from last Thursday. So think about this one here is the from, let's say, for example. And then from is going to correspond to, for example, the top. So you can think about from here is from here. Okay, just one example. And then this one here will be the bottom. All right. This will be maybe the 2 index. So think about the 2 is the bottom one here. So we got from here, we got 2 over here. So there will be another special case will be the second last disk from the bottom. This one here, like a second largest disk. And that one there should be of index 2 minus 1. Okay, we're going to need it later. So this will be 2 minus 1. So think about this another disk over here. That's 2 minus 1. Okay, so when we program in Java, we got to work in terms of the array. But conceptually, you got to see the correspondence to the tower. That's why I'm also drawing that, right? That's important. All right. And then let's now try to analyze the call over here. So in the beginning, when we call this so-called recursive helper method, let me remind you about the term. It's a helper method, but it's also recursive. So this is a recursive helper method. And call by value, we're going to pass the reference of the array. That's the same. And in the beginning, we say that we want to pass the entire tower. So this part here, you can think about what we're doing is, let's say 0 to disks.length minus 1. That's basically going to cover the entire range, right? From 0 all the way to the length minus 1, right? That means it's going to cover the entire tower. Okay, entire, from the top to the bottom. Of course, later on, we're going to, for recursion purpose, we're going to subdivide that into sub-tower and the bottom, right? That's what we'll do later. And convention here for 1 and 3, that's important, okay? So the 1 and 3 here are about the packs, okay? So here, 1 and 3 is about the packs. Think about the pack. We got pack number 1, pack number 2, pack number 3. Okay, but in Java, when we pass the value, we just pass either 1 or 2 or 3. Right? That's something to remember. So let's now think about how to interpret this recursive helper method call. We pass the disks over here, which represent the tower that we're trying to solve. And we say that in the beginning, we want to solve the entire tower from 0 to the end. That's basically the entire array as a range, or the entire tower. And where do we want to move it from and to? We want to move that from pack number 1 to pack number 3. That's how we interpret that method. All right? So I say the trickiest bit about this lecture here is to understand how the Java code itself corresponds to how you solve the puzzle on the paper. That's the most critical insight you want to convince yourself. All right, any question so far? All right, that's good. So this one is nice. And then let's now talk about the recursive helper method itself over here. Okay, it's called TOH, Tower of Hanoi helper. Again, we pass the disks over here, called by value, and we got from and to. So think about here, it's going to be from and to. Oh, sorry, let me do that. That's what I meant to draw. So from and to. So this one here really corresponds to this part of the array. I want to just, oh, sorry. Let me do it again. We don't divide just yet. From and to. Okay, from and to is actually going to cover the entire thing to begin with. Okay, that's good. And then we're going to move from origin to destination. This could be some value. And the value for origin could be 1 or 2 or 3. This one can also be 1 or 2 or 3. It depends. All right. From the origin to destination. And the two base cases should be quite straightforward. When you got from larger than 2, as we said, that means empty range. That means no disks to really move. So no step. Don't print out any step. On the other hand, when from is equal to 2, for example, if I say I just want to move this one here, so that'll be from and to just being equal to this 0, for example. In that way, I will simply say I want to move something. Okay, for the details, I'm going to do the tracing in a moment, but that's something you can also look at, right? Just remember, from and to tells you only one disk to move. So this is definitely a very important base case. So this one here tells you only one disk to move. Only one disk to move. All right. All right, let's now talk about recursive case. That's the most critical bit, right, to understand. And if you recall the strategies I talk about over here, right? Step number 1, number 2, and number 3. All right, and we got exactly that. Okay, I'm going to label them first of all. This will be number 1. This will be number 2. This will be number 3. And I'm going to visualize each one by one. All right. And one thing very important to talk about. Let's say, for example, if I want to move the entire tower from P1 to P3, in that case, the origin and destination will be 1 and 3. Right? If I want to do that, from 1 to 3. And when we divide the problem, we're going to take the sub-tower over here and move that recursively to the intermediate tower. Now, how do we know computationally what an intermediate tower is? When we go from 1 to 3, 1 and 3, the intermediate ID should be 2. Because 1 plus 2 plus 3 is 6. So we know that if we know the numbers for the other two, we can subtract to get the final one. All right? That's really important. So now intermediate in this case will be 6 minus 1 minus 3, which will be 2. Again, this tells you if my origin and destination is 1 and 3, I want to move from pack number 1 to pack number 3. The intermediate one for me to play with during the recursion will be number 2. Let me give you another example. What if I got, let's say, I want to move from 2 to 3. So conceptually, I want to move the entire tower from 2 to 3. What will be the intermediate one? Number 1. How do I calculate it? 6 minus 2 minus 3. I'll get 1. All right. That's something you have to also convince yourself. That's a very critical calculation. And we can do this simply because we got 1, 2, and 3 only, always. Okay. All right, so now let's take a look at these 3 over here, which is very interesting. All right, I'm going to visualize them one by one. Okay, it's important. And number 1 here, and before that, let me tell you the starting phase, the starting states. For that, let me copy this. Put here. Okay, that's what we start with. Oh, sorry. There we go. Okay, that's what we start with. And this one tells you we're going to call the Tower of Hanoi helper recursively. That's the first recursive call. Disks over here, just call by value, the same. Now, from n to -1. That one there tells you you're actually going to, okay, let me use a different color here. That one there tells you I'm going to go from to 2 minus 1. So from to 2 minus 1, that's the array. What does that correspond to in the actual tower? So from to 2 minus 1 is going to go from the top all the way to everything except the bottom layer. So that one there basically tells you that's this one here. Okay, if I want to make it more explicit for you, that's orange. So that's the tower I want to get. All right, conceptually. I basically want to move this sub-tower over here, which will be here. I want to move that one there from origin to intermediate. All right, the origin is here. The origin is where we start from. This is the origin, so this is the destination. And the intermediate is going to be using the formula I just spoke about, right? The intermediate is going to be this one here. So what I would do is for stage number 1, I'm basically going to recursively move this one over here. Okay, let me see if I can do it in one go. All the way to here. That's what we're doing. Okay? If you get about 50% understanding, that's great. It's a challenging problem, right? Just it's going to take some time. All right, so that's stage number 1. So stage number 1, we have moved this guy here. That used to be here to the intermediate one. And stage number 2 is going to be, you can also think about it's more like a base case. It doesn't require any recursive call. From there, we're going to say disk 2, okay? So this one here, disk 2, is corresponding to basically the bottom one over here, right? And also, it's basically just this part, the last bit of the array. Okay? And we're going to move that from origin to destination. Okay? How does that work? So let me just copy this one over here, and then I'll show to you. Just don't forget, stage number 2 follow after stage number 1. So what we're going to do is we're going to move this bottom disk, which is the largest, from origin to destination, right? From origin to destination. This one here, which is here and also here. Right? All the correspondence is clear. Finally, we got step number 3 here, phase number 3. This is just another recursive call. Because if you look at the end of stage number 2, we have not quite done yet. We got this sub-tower over here in the intermediate pack. What we want to do is, again, recursively move it from pack number 2 to pack number 3. And in this time, when we want to go from here to here, this will be the origin, and this will be the destination. Right? So the origin should be right here. You will switch. So when we do the tracing, you will see that the origin and destination are not necessarily always 1 and 3. It does change. All right? All right, so let's now try to understand the final bit over here. Okay? And from and 2 minus 1 is basically the same. So let me just use, how about purple? Okay, from and 2 minus 1. That basically tells you we're just going to consider the same range for the second time, right here. All right? And then think about that one there is going to talk about this tower here for the second time. Okay, right here. Just this tower. just for the second time. All right, you can see we consider the first time, which is the orange, the second time, which is the purple. All right. And then we're going to have stage number 3. Okay, let me copy that. So this will be the starting point over here. All we got to do is simple, conceptually move this guy here from here all the way stack on top. That's the third phase. It might seem a little bit magic to you, but that's really the nature of the recursion. When I say I want to move this guy here from here to here, I assume I have a solution. That's really the spirits of recursive design. How exactly it's going to work, we'll see that in the trace. All right, in a moment. All right, so this one here, of course, I can just make it purple, so you will see that exactly consistent. All right, one thing to note when you study for the solution, you want to notice that here we got the destination being the intermediate. And also here, the origin being the intermediate. The reason is, when I want to move this guy over here, I want to move that from here into the intermediate. That's why the intermediate is the destination. On the other hand, when I'm here about to start, about to start stage number 3, so here the sub tower here is going to be moved from the intermediate here, being the origin now, into here. That's why I got intermediate here. All right, just notice that. That's something you want to convince yourself as well. All right. Any question? Hopefully, at least the big picture is clear, right? So once you can see, we basically have repeated the strategy the second time already. The first time is when I actually try to demonstrate to you on the diagram about how to solve the problem informally. The second time is when we analyze the Java code. Now I'm going to do that the third time, which is to trace the code. Okay, and I'm not going to do using the call stack. It's going to be too confusing. Nobody can do it right live. Okay, what I'll do instead is to show the high-level tracing, which is going to be beneficial. Okay, for you. All right, let's now take a look at the tracing here. All right, and you will also see the solution over here in the slides. But I'm going to do it from scratch, so you can really see the build-up process. Okay. All right, let's now say we got disks over here. That's called the DS. Right? It's a call by value. And let's say we got A, B, and C. We got A, B, and C over here. And also we got indices 0, 1, and 2. All right, let's have some convention here. So the way I'm going to visualize, let's say A is going to be green. And B is blue, and also C is kind of orange. So I'm going to start with C here at the bottom here, and B over here, and then A will be green. Oh, should be smaller. Like that. Okay, that's my starting point. So think about this one here is the original problem. Original problem. And in order to solve this, we're going to see that when we try to show the tracing over here, we're going to see exactly subproblem number 1 and subproblem number 2. That's what we'll see in just a moment. Okay, let's now try to get started. I'm going to skip the starting point here. Okay, let's see exactly how the recursive helper method is going to do. Okay, so let's start right from there. All right, I'm going to call that Tower of Hanoi helper. So Tower of Hanoi helper, I'll say H. And then I'm going to pass call by value the disks referring to here. And then in the beginning, I want to cover the entire array. That means I want to solve the entire problem. It's going to be from 0 to 3. So right here, you can see 0 to 3 is corresponding to A, B, and C. And that's really corresponding to the entire tower. Right away, we can see that. And then where do I want to move it from and to? I want to move it from pack number 1 to pack number 3. In the actual programming, you will say 1 and 3. But let's make it a little more informative for you on the paper. So why don't I say P1 to P3? Okay? So you can see, even though these four things are really all integers, but they represent different things. So these two are the range specifying the tower that we want to solve. And these two are the origin and destination packs that we want to move from and to. All right? So this is the initial call. And apparently, this problem here is too big to solve. So what we do is we're going to divide that into three phases. Phase number 1 and phase number 3 are going to be recursive calls. Phase number 2 is going to be something very quick to be done. All right, let's now try that. So phase number 1 is going to be, also we're going to call Tower of Hanoi, helper, and then call by value just the same array over here. And now I want to specify just these two, the subtower, everything except for the last. It should be basically A and B, 0 and 1. Agree? So it's going to be 0 and 1. And think about 0, 1 is covering only these. 0, 1 is only covering these. Okay, like that. Okay. And I basically want to move from here into something intermediate. Not really to here just yet, according to strategy. All right? So what I will do is I'm going to say from P1 to P2. And one thing to note, P2 over here is the intermediate. And you can think about the P1 over here and the P1 over here. These are the origin. And for later, this one is the destination. Destination. Okay, that's the first phase. And we're going to talk about this in just a moment. This one apparently has not reached the base case just yet because this subtower here is still too big for me to solve right away. All right, how about phase number 2? Phase number 2, we're going to move the bottom one over here to here. All right, so let me annotate here quickly. So also we got subproblem number 1. Right, that one over there, let me just show to you. That one there is about moving this guy over here into here. Right, you want to move from here into over here. Okay, that's a subproblem number 1. And for subproblem number 2, we're going to move this one here back on track into here. All right, that's something we'll see later. Okay, let me just put it over here, so that's complete. All right, so what about the second step? Second step, we can simply say move. Since we talk about A and B here, so the one that's at the bottom here is C. All right, so we can simply say move C, and then you want to move that C. So once these two have been moved to here, so we want to move C from the original pack number 1 to pack number 3. All right. So from pack number 1 to pack number 3. Okay, that's phase number 2. And phase number 3 is going to be yet another recursive call. Tower Hanoi helper. DS, call by value. And then we still want to move a strictly smaller tower here from basically intermediate onto over here. So conceptually, we're going to stack it on top. So think about that's going to complete the puzzle, right? That's what we're going to achieve. That's something we're going to move into over here. So that's subproblem number 1. Sorry, number 2. Subproblem number 2. All right, so what do we specify? We still want to get A and B. So let me say we're still going to cover A and B, which will be 0 and 1. So we're going to get 0 and 1, the same size of the subproblem. 0 and 1. So look at 0, 1 here, 0, 1 here. That's okay, the same tower. And then what about origin and destination? All right. If we're here, that's the beginning stage for subproblem number 2. We basically want to move this from here, stack on top into here. That'll be from P2 to P3. Agree? All right. From P2 into P3. And again, notice that P2 over here is the intermediate. And P3 over here is the original destination. Let me do a quick highlight right away. To solve this problem over here, to go from P1 to P3, so P1 and to P3, we have to first go from P1 to P2, P1 to P2, and then from P2 to P3. Right? That's exactly what's showing here. But you want to make sure when you go to the intermediate one, it's got to be a strictly smaller tower. Otherwise, you get infinite recursion. All right. So this one here will be stage number 1 over here, stage number 2, and also stage number 3. So in order to execute this, we need to execute this, followed by that, followed by that. It's a little bit similar to Fibonacci sequence, if you recall. We say, for example, F5 can be F3 plus F4. In order to really calculate this, I need to first calculate F3, which might involve certain recursion here. And then after this is done, I can go on to F4. Similar. You can only get to phase number 3 after the previous 2 phases are done executing. Question, please. I agree. Absolutely. Thank you so much. It's definitely a terrible typo for me. Yeah, this one here should be 0 to 2. Absolutely. Thank you so much. There we go. Thank you. Yeah, for sure. All right, so this is what I'm going to do. I just want to show to you how this branch over here can finish executing. We're almost there. Oh, I said 3 again. Funny enough, I thought 2, but somehow I write 3. This is 2, right? Okay, good. Thank you. When you somehow too much into tracing, you don't really recognize numbers anymore. Thank you. I really meant 2. Okay. All right. All right. All right, so guys, here's the deal. I'm going to finish executing this guy over here, and then give you some idea. And then this part over here, give a try. All right, to finish this part. You can see the solution on the slides right here. Okay. Let's now do this one, just to give you more idea. And this one here is saying we want to move the tower of 0, 1. Basically, this sub-tower over here. Okay. The phase number 1 is trying to move from P1 to P2. So P1 to P2. In order to do that, we need to make use of the intermediate one, which will be P3. All right. In order to move from P1 to P2, you need to use the intermediate P3. All right. Let's now take a look how that's going to work. Okay, so we're going to say tower of Hanoi, helper, and then call by value over here. So now if I want to move this tower over here, let's say, so bottom 1, and then the rest. And we're lucky the rest here is only one single element tower, only one single disk tower. All right. So that one there, I'm going to put 0, 0. And I want to move from P1 to P3. Okay. This one here tells you I want to first of all move this one here into here. Okay, that's what I would do. And then after that, phase number 2, I want to move the rest. Think about this tower here. First of all, I move the sub tower into here. And then move the bottom part over here into the intermediate one, which is over here. All right. So this one here will be move the disk B, which is exactly over here. All right. B, and then you'll be from P1 to P2. All right. Phase number 3 will be similar. I think once you have got this level here, you're pretty much getting almost everything. I think this one here just further practice. So that's why I'm doing that a little bit more quickly. Tower of Hanoi. So this over here. So the same sub tower. 0, 0. So you can think about 0, 0, 0, 0. It's basically, oh, you know what? I should really use green. 0, 0, 0, 0, just corresponding to this 0 over here. All right. And then it's going to be from intermediate P3 back to P2. So after all these steps, here, we will have achieved moving this into over here. So think about from here to here, conceptually, it's only one step. But concretely, it's going to be 3 individual steps. All right, that's something you got to pay attention to as well. And this part over here is going to be exercise for you. So this part over here, it will be some exercise. There will be something you got to trace. And I'm going to make a final comments. So think about how this tracing is going to help you. Since I know that in order to calculate this original problem here, I need to calculate this one first. In order to calculate this one here, I need to calculate 1, followed by 1, followed by 1. And by the way, 0, 0, 0, 0, if you see that, exactly the base case. All right? And this one here, you can think about it is step number 1, number 2, number 3, and then the number 4. And once you do the exercise, you will see 5, 6, and 7. And in order to solve this original puzzle over here, you will just need to follow through 1, 2, 3, 4, 5, 6, 7. All right, that's what you will need to follow. And if you go back to the Java code, over there, you can see no surprise. 1, 2, 3 is something we just traced. You can double check. Number 4 is the phase number 2. And 4, 5, and 6 are the phase number 2. Sorry, phase number 3. All right, some details to be understood. Maybe I got to spend some time understanding this. All right, any question about the tracing here? It will take some time, okay? But if you understand roughly about how things go, you just need to work out the details a little bit more. Oh, just one more thing to say. You might be wondering, oh, how about this method call? Since already reached the base case, so this one here is easy to work out. 0, 0, that means it's referring to pack A. So you're going to move A from P1 to P3. There's no intermediate. It's a base case already, okay? P1 to P3. And this one here, move A, P3 to P2. All right. Okay, that's about the tracing. All right, so the final thing I want to do about the Tower of Hanoi, this is something that's not going to be covered in your exam, but for you guys' information. So what we have done so far is pretty standard for how we understood programs in this course. We're going to talk about some conceptual sketch, right? That's how we started with. And also we did the Java code analysis over here, understanding how it is supposed to execute step by step. And then we try to execute, trace some actual program, some example run. What we didn't really do in this course is to analyze how efficient the solution is. And this will not be such a concern in this course as long as your program terminates, we'll be fine. But in 2101, next semester, about the data structure, we're gonna study a catalog of different data structures. Every time to solve a single computational problem, you got simply different alternative data structure you can choose from. Which one should you choose? You should choose the one, number 1, that can be correct. Number 2, that can solve the most efficiently. So now I'm going to give you some idea about what efficiency really means in terms of time. All right? And I'm not going to touch something well, of course, to do it formally, you got to use the big O and also asymptotic upper bound. Let's not worry too much, right? But I want to give you some intuition. But we're going to need a little bit math, a little bit, not too much. All right, so let's say this. Let's make the following assumption, okay? Let's say I'm trying to solve this problem here. Of course, for people working back in India, they get a 64 disks, right? It's gonna be a much bigger problem. Can we make the following assumption? To move one pack from to move one disk from one pack to another, it takes 1 second. Reasonable, huh? Reasonable, okay? For one person, just 1 second. And now the question is, if I give you n disks, can you tell me how many seconds it's gonna take for you to complete the puzzle? For example, let's say for this problem here, if I give you 3 disks, it took 7 steps. That means 7 seconds. So what about 8? We're gonna calculate. What about 64? We're gonna make that conclusion later. All right. What I'm gonna do is I'm gonna make a formula to tell you, given n, I can tell you exactly how many seconds it's gonna take. All right, let's now see how we can derive that. It'll take about 10 minutes. Okay, let's do that. All right, so I'm going to have this called a runtime function, t. Okay, it's a standard notation here, t standing for time, running time, runtime. Let's say seconds. And the input it's going to take will be the number of disks. When number of disks is simply 1 second. Move from 1 to 3, right? Simple. What about when it's equal to n? For that one there, we're going to find the corresponding recursive case over here. All right? So you can see we were basically doing recursive case number 1, and also we're doing recursive case number 2. All right, well, conceptually, you can think about, in order to move this tower, I need to, first of all, move the sub-tower from here to here, and then the the sub-tower from here to here, and then the same sub-tower from here to here. I got to do it twice, okay? So you want to think about what's the problem size. So since we talk about from and to minus 1, from and to minus 1, I got exactly 1 less disk to handle in the sub-problem. Agree? So think about the original problem here, which would be from and to. That one there is more like a t of n. And over here is going to be t but n minus 1. I got 1 disk less. This one here is also t n minus 1, the same, recursive call. And what about the one in the middle? This one here is like moving the bottom disk from one pack to another, 1 second. So if I sum this up, it's going to be 2 times this plus 1. All right? So that's how I work out the equation. So 2 times t of n minus 1 plus 1. This will be something that you guys will have to somehow derive for 2101, especially for searching and sorting algorithm. That's something we'll talk about, don't worry. I want to give you some look ahead. All right, so now I still don't have the formula. I need to somehow derive the formula from here, okay? So I'm going to do something called unfolding. Okay, so what I'll do is I'm going to start with t of n, the original problem here. That one, by definition, is going to be, let's say we haven't reached the base case yet. It's got to be exactly 1 for that to be qualified to be a base case. So it's going to be 2 times t of n minus 1 plus 1, right? So what I'm doing here is just copy this formula here. This one here is this one here. Okay, the first step is the most critical. Think about n minus 1 is just one instance of the same problem, except rather than n here, I can plug it out by n minus 1. This one here by n minus 1. Right? I'm pretty sure that's something you did maybe in the linear algebra course, right? Something similar. So what I will do is I'm going to say that'll be 2 times something here plus 1. So this guy over here is going to be, I'm going to replace n minus 1 for every occurrence of n. So notice that here it's going to be n minus 1 minus 1, n minus 2. All right? So I will get t of n minus 2 and then plus 1. Okay? Oh, I'm missing something here. Apparently, I'm not very good whenever I talk about number 2. And don't forget, there's a 2 here. All right? That's precise. All right, let's unfold one more time. The reason that I still want to unfold is because n minus 2 is still too big. I haven't reached 1 just yet. Okay, let's do one more. So what I will do is I'm going to actually talk about unfolding this guy over here. What I will do is I'm going to substitute n minus 2 for every occurrence of n minus 2. So that means n minus 2 minus 1, n minus 3, right? So I'm going to do this 2 times plus 1 plus 1. All right, and I'm going to fill out something here. So if I replace it, it's going to be t of n minus 3. Again, I forgot about 2 times. All right, don't forget, there's also 2 times here. 2 times n t of n minus 3 plus 1. Okay, now you cannot just keep unfolding this indefinitely because it wouldn't get anywhere. As soon as you have unfolded the running time formula there for a few times, now your job is going to observe some pattern about how the unfolding can potentially reach the base case. Okay, I'll give you some hints. As you can see, we got 3 here, right? Coincidentally, here, 2 times 2 times 2. 2 to the power of power 3. Plus 1 plus 1 plus 1. Plus 3. Somehow, this number here corresponds to exponent and the constant factor over here. Somehow. I can verify this again. 2 here, 2 times 2. 2 to the power 2. Plus 1 plus 1 plus 2. You can see 2 here matches 2 and matches 2. And also 1 here, I got 2 to the power of 1 plus 1. 1 matches the exponent and also the plus 1. Looks like a safe pattern to conclude. All right, so this tells me every time I try to do unfolding for one more time, I'm going to reduce the n value by 1. So I go from n minus 1 to n minus 2, n minus 3. Now I want to ask myself, how many unfolding do I need to do? N minus question mark over here is about the number of unfoldings. I want to reach the base case 1. So this is the most critical number to work out. Any idea what the question mark should be? N minus something is going to be equal to 1. Guys, that should be easy mathematics, right? I'm pretty sure you know. You're just shy. Go ahead. Just n minus 1. Yes, that's correct. All right, I'm pretty sure you guys know, right? And what your classmate said was also correct. Right, double check, right? This will actually work. This one tells me that I can say 2 times 2 times 2 all the way to, I can eventually get to t of 1, and then I can say plus 1 plus 1, plus all the way to 1, something like that. Okay? So this one here is the base case. I know that it's 1. And this part over here, I know that the number of unfoldings I need to do is n minus 1. So that should be 2 to the power of n minus 1. All right? And this part here, also I know that that one should correspond to the number of unfolding as well. That should be plus n minus 1. All right, let's now write this aside and make a conclusion. Since we have done so much work. Ultimately, this one here is going to be 2 to the power of n minus 1 plus n minus 1. This is to say, if I tell you I got n disks in the Tower of Hanoi as an input, it will take this much second to complete the puzzle. Right? Of course, you can plug in some specific number. We'll do that later. Okay, so now, for those of you who took 1019, for example, you learned about big O, just for your information, we can drop this term here because asymptotically, exponential is going to dominate over linear. That's something we'll talk more in 2101. But you can say this one is approximately 2 to the power of n. Approximately. Okay. All right, so let's now make a conclusion. Let's go back to the puzzle, right? So what we have done in terms of mathematical analysis can really kind of answer our doubts about when is the world going to end, right? That's a question we want to ask. That's a Java code. That's the unfolding. That's a running time. All right, back to this legend here. Oh, we make the assumption one disk take 1 second. And since we got 64, so now it should be 2 to the power 64 seconds to complete. Any idea how long this will take? Quite a lot, actually. It takes this much time. More than 5 billion centuries for them to complete. So I think we are fine. It will take them quite a while to finish that. So don't worry, you can still finish your exam on Sunday. All right? Not a concern. All right? Anyway, so that's the Tower of Hanoi. For the exam, you don't need to worry about the mathematical analysis I just went over. Don't worry about it. But that one there just give you some idea about what you have to do in 2101 next term. Okay? This one, don't worry. But what you should really spend some time is about tracing and also the Java code, since we covered that. All right? That one I'll leave to you.